Okay. All right, so last bit we're going to do in this section was talk about strong induction. Okay, so this is similar to the inductive process, with one important change. Okay, so again, we're sort of looking at a proposition, and we're going to have a basis step. Say if pk naught is true. And we're sort of using pk naught here instead of p1 because we saw that that beginning, the number in the basis step is a bit fluid. It kind of depends on what problem we're doing. So pk0 is true. So it could be 0, it could be 1, it could be 25, depending on the problem. And the inductive step is what's different. It says that for all n is bigger than or equal to k naught, we're going to assume that all previous statements are true, and that will lead us into Pn plus 1 being true. Okay, so just assuming that Pn is true for some problem is not sufficient to get us to prove Pn plus 1. So for some problems, we need to assume that all the previous propositions that came before it is true and go to there. But the same principle of sort of that domino effect comes into play. And sort of this is, you can argue that strong induction is a valid argument, valid logical argument through using the chain rule laws and the laws of logic. All right, but let's see how it works in practice. So show that if n is an integer greater than 1, then n can be written as a product of primes. Okay, so let's start with the basis step. The basis step is p greater than 1. So we want 2, okay, because we're looking at greater than 1. We're looking for n is bigger than or equal to 2. And because 1 is not prime itself, it doesn't make sense to start at 1. Okay, so we have, I know that 2 is equal to 2 times 1. So they're both prime. So it's written as a product of primes, except the 1 is, yeah, anyway. So yes, so it's a kind of, if a number is a prime, it's written as a product of the number by itself. So you can sort of say that it's written as a product of primes. All right. Now the inductive step. Okay, we're going to assume that all these statements are true. So P2, P3, Pk. Okay, so all these are true. So 2 can be written as a product of primes, 3 can be written as a product of primes, 4, 5, 6, 7, 8, all the way to k. We're going to assume that all of these can be written as a product of primes. And we want to show Pk plus 1. We want to show that this is true. All right, so basically this means, can I take this integer pk plus 1 and write it as a product of primes? All right, so here's the argument. So here's how strong induction works. And strong induction uses a lot more words than equations. All right, so we consider 2 cases. So we have case 1. So case 1, you have that k plus 1 is prime. If k plus 1 is prime, then k plus 1 is going to be k plus 1 times 1. So that basically proves it, because this is the product of primes. Okay? Case 2 is k plus 1 is not prime. K plus 1 is composite. If k plus 1 is composite, then k plus 1 can be written as a product of 2 integers, L times M. All right. And what I know is that both L and M are going to be less than k plus 1. Right? They have to be, because if they're the same as k plus 1, then we're sort of back to case 1. Now, because L and N are less than k plus 1, then this kicks in. Okay, I know this sort of, I'm assuming that all the integers that are less than k plus 1 can be written as a product of primes. So because L and M are less than k plus 1, L can be written as a product of primes. And M can be written as a product of primes. Right? And that means that L times M are going to be the product of primes for L and the product of primes for M. So L times M is a product of primes. Okay, that's it. We're done. That's basically what we're trying to show, that k plus 1 can be written as a product of primes. All right, but notice that sort of for this problem, it's not enough to just use that pk is true. We had to use that not all the others, but some of the others, some of the other previous statements were true. This sort of random numbers, integers L and N, they didn't need to be immediately before the k plus 1. They could be sort of anywhere from the start, the basis step 2, up to k. All right, and that's it for strong induction proof. All right, example 10 there, I'm not going to do because basically this is your project 1 problem. But this, you want to tackle this using induction or strong induction. Actually, strong induction is probably what you want. And sort of make a similar argument that we've done in this strong induction examples in this section. All right, so I'm going to pull up example 11. All right, so example 11 says, prove that every amount of postage 12 cents or more can be formed using 4 cents and 5 cent stamps. All right, so let's look at the basis step. Okay, so 12 cents or more, that means I'm looking for n is bigger than or equal to 12. So we're going to take our basis step to be when n is 12. Okay, so I have 12 cents. Okay, and I want to show that it can be formed using just 4 cents and 5 cent stamps. Okay, so let's see. I can do 4 plus 4 plus 4. So 4 plus 4 plus 4 cents makes 12 cents. So it's possible. All right, so that proves the basis step. Now the inductive step. All right, so this is a strong induction proof. Inductive step, we're going to assume that P12, P13, P14, all the way to PK is true. Okay, so we're going to assume all these postages can be made just with 4 and 5 cent stamps. And we need to show that PK plus 1 is true. Right. So let's look at PK plus 1. So PK plus 1 means that k plus 1, this integer number, can be made up of by adding only 4s and 5s. Right. So I'm going to say, well, k plus 1 can be made up of m plus l. Okay, so I'm going to take 2 integers and those will add up to give me k plus 1. Okay, so the important thing is, it's like, I don't really care what they are. What I care about is that both m and l are less than or equal to k plus 1. Right. So because these are smaller than k plus 1, then they fall in this category. All right, so they fall in this category. That means that M can be written as a sum of just 4s and 5s. So M is equal to just the sum of 4s and 5s. And also L, because it's less than k plus 1, can be written as just this, maybe the sum of just 4s and just the sum of 4s and 5s, like this. Okay? And because M is formed out of just 4s and 5s and L is formed out of just 4s and 5s, if I add these up, M plus L is going to be the sum of just 4s and 5s. Okay? And M plus L is my k plus 1. All right, so that completes that proof. Okay, so kind of just looking at two random numbers that are less than k plus 1. Because they are less than k plus 1, then that statement is true. And when you sort of put them together, that statement still remains true because the sum of them is going to be made up just of 4s and 5s. Okay, so that's the strong induction proof. Again, strong induction is a lot more words rather than equation, sort of arguing that sort of we have these integers and they're true, therefore added together, they're going to be true. All right, so that's the end of this section, the section 3.7 on induction. All right, so please, hopefully you sort of made some notes throughout the lecture and come to the live session and ask me questions, and we can go over problems in more details and clarify some things. All right, bye for now.